Welcome to my MiSTer2MEGA65 Tutorial Series. My aim is to explain the basics of the M2M framework by doing an example core port. If you don't know what the M2M framework is, take a look at my MiSTer2MEGA65 explained video. In short, the M2M framework is a hardware abstraction layer with which MiSTer cores can be adapted to the MEGA65 hardware. To be able to follow this guide, you need a MEGA65, a PC, and ideally a JTAG interface. You should also have some knowledge of programming and electronic design. I'm using Linux as the PC operating system for my tutorial, because that's what I'm most familiar with and as it is freely available. However, it shouldn't be a problem to follow the instructions using a different operating system. The individual episodes of this tutorial build on each other, so you should start with the first episode. Let's start! My tutorial will follow the instructions in the M2M wiki. So let's take a look at that first. The first step, what is the MiSTer2MEGA65, is already covered by my MiSTer2MEGA65 explained video. So we take a look at first steps. And here we see some requirements in the beginning. It tells us that we need to have a GitHub account. Okay, I already have one, and I guess most developers will also have one. If you don't have one, you can create one fairly easily. The free plan is enough to do work with it. Then you need a GNU compiler chain with GCC and make, and you will also need the Git command line installed. And most Linux and Mac OS systems will already have that. For Windows, you can use the Windows Linux subsystem. Then you need Vivado, which I already made a video for. And you need a MEGA65 R3 or a dev kit, which is also the R3 board. So the MEGA65 is the R3A board. And you also should have a JTAG adapter, because that makes everything much easier when it comes to testing cores. So how should we start? Let's read step 1. So we should use the template functionality of the repository. So we open the repository page, then we need to sign in. And now we have the use this template button. We click it and choose a name for the repository. I'm choosing the recommended my first M2M, and I make it public, and then I create my new repository. So, but this repository is only on GitHub now. In order to work with it, we need to clone it to our machine. So let's take a look how this works. And here are the commands to do it. I change to my MEGA65 development directory and then clone. Yeah, but I need to clone my repository. So I will use this nice clone button. You can choose between HTTPS and SSH for this. I normally use SSH. And then I clone the repository. Now it's there. And the next step is to change into the directory and initialize the submodules, which is the QNice repository, which is the extra processor the M2M framework uses to do, for example, the on-screen display. We will leave out the remote add command, because we don't plan to update this, so we don't need it here. What's the next step? Next step is making the toolchain. So let's do that. This make toolchain will build some stuff needed by the rest of the build process. For example, it builds an assembler for the Q9 CPU. And there's one step where it will ask you a lot of questions. You just press return and take the defaults. So now we have it. We can check if it was correctly built by looking for the monitor ROM. Yeah, it's there. Wonderful. So then we can start building the core. And the first step to build the core is to change around to the core subdirectory and there into the M2M ROM, and then call the make ROM script. There's no make file for this, so you have to do it by hand. Make ROM, yeah, very fast, already written. Good, next step is go to the core and open Vivado here. So I will now open Vivado in my menu. This takes a little while. There it is. And then we will choose, let me make it a bit bigger. Then we will choose Open Project to open our project, and it is in Mega65, and there is my first M2M, and it tells us we need to open the core R3 XPR, which is in the core subdirectory. The XPR file is the project description file. And now we create the bitstream, and this can be done by pressing on this side on the generate bitstream button. And here we can see the synth is running. And this will take a little while. So it's finished with writing the bitstream. We don't really need to open anything of this now. Let us first take a look on the timings, and you can see it took 3.5 minutes to run the synthesis and 2.5 minutes to run the implementation. That's quite fast, but it's only a small core, so was to be expected. And now we can try to get the bitstream on the FPGA. Step 4, run the core. We will try out multiple ways to get the bitstream onto the Mega65. So let us get a picture of the Mega65. I'm running the C64 core right now. And then we will do it with Vivado first. So to do this, we open the hardware manager, and in the hardware manager we get this new window with the open target menu, and there we select auto connect. This will open the USB, and I have already set this up so it directly finds my Mega65 behind the JTAG interface, and it is programmed. Obviously the C64 core is running, and I can now press program device either here or here. Choose the FPGA. It will automatically choose the bitstream that was created in the implementation run, and then we just press program. And there you can see the Mega65 is running the bitstream of the Democore. Okay. So let's see if we can do it the Mega65 way. For this, we should be in the core directory. And here we have the path we saw before. And we use Mega65 tool with -q, -q. And in the core R3 runs directory implementation, there's the core R3.bit. And if I press enter, it won't work because I have still opened the hardware manager in Vivado. So let me get this out of the way. And now the same happens. We could see the picture was gone for a short moment and then it reappeared as the Mega65 tool did also write the bitstream. Now to the last method, which would work without JTAG interface. For this, you need the bit2core utility from Mega65 tools. And it needs some parameters. The first is the target, which is Mega65 R3. Then it also wants to have the bitstream. And now we can give it a core name and a core version. So it's my first M2M and it's version 1 and output file. And this should have written a core file. Yes, wonderful. So to get the core file onto the Mega65 via the flash menu and then booting from the flash menu, I have this all covered in my core installation tutorial. So take a look at this. It takes a bit longer because you need to copy it to the SD card, put the SD card into the Mega65, then flash the core to the SPI flash and then boot from that. So a JTAG interface is really recommended. You should be using that. So the first step, how-to wants us to play around with the resulting core a bit to see what the Democore can do and what we can do with it. So first we see a welcome screen with some default text and a bit of explanation which keys do what. I think this is mostly copied from the Game Boy core. Yeah, it even tells you that in the text. So with a space, we get rid of this and you can see we have a nice scrolling background and a pedal and there's some sort of ball in the middle, the red thing. And there are some hearts. And what the explanation at the beginning also told us was to press help to get a menu. And here we can see various items and menu items. And yeah, I guess the upper ones are just for showing off that these are radio items. This one actually should do something. Yeah, it switches to 60 Hertz. 60 Hertz looks a bit odd perhaps because my Atem Mini is set to 50 Hertz. Then we have drives, and when we press enter we can mount some image from the SD card, but that won't really do anything, just it will mount it and then display the name of the mounted image, but you can't really do anything with it because the Democore can't use drives. And we could also use press space to unmount again. Yeah, works. Then we have CRT emulation, which actually does something. And the HDMI zoom in also works. Perhaps it zooms a bit too much in. Audio improvements, I'm not sure. Okay, and then we can close the menu with this menu point. And now we play a bit with the breakout. And I will turn the sound on because I think there's supposed to be some sound. Let's try this. Ah, okay. A rather particular sound. Oh, and it changes frequency with the ball, it seems. So we can move the pedal and we can bounce the ball, but we have no tiles to, break, essentially. And yeah, the sound is really getting on my nerves, I think. So let's... oh, no, I did not hit the ball. Okay, away with the peeping sound. Perhaps this could also be a good test that we try to get rid of the sound via the menu. But that's also something for the Hello World part of this tutorial. Okay, I think we've seen everything. On to the next part. Now that we have gotten a first glimpse of what M2M can do, it's time to go one level deeper and to look at the structure of the framework. The basic structure of the M2M core consists of 2 or 3 parts, depending on how you count. The first part is the M2M framework itself, and it can be found in the M2M directory. This part you should not touch. The second part is the core, which you will find in the core directory. Here you will be doing most of the work, adapting the MiSTer core to the MEGA65 hardware through the M2M framework. The third part is your fork of the MiSTer core, and it will be placed in a subdirectory of the core directory. You should keep changes to the MiSTer core at a minimum, so you can easily incorporate upstream changes. But sometimes you have to change something in the core because Vivado does things a little bit different than Quartus does. Top MEGA65 R3 VHD is the top file for the whole machine. The R3 tells us that it is intended for a MEGA65 R3 board, as it can be found in the dev kit or in the release machines. To support the architecture, there are 2 additional files in the core directory. Core R3 XPR, which is the Vivado project file we did open to build the bitstream, and Core R3 XDC, which is the constraints file that contains I/O mappings and definitions for time enclosure. The core instantiates only one other entity, which is the M2M framework. This glues together the M2M framework and the core of your project. To do this, it instantiates iFramework, which in itself contains things like analog and digital rendering pipeline, the HyperRAM controller, and the QNice CPU. On the other hand, M2M also instantiates your core. It is the top file of the user space and a lot of things happen inside. It is responsible for clock domain crossing hardware, such as RAM, ROM, and other devices. It implements device-specific logic, it handles on-screen menu logic, and it handles the wrapper to the MiSTer core. In the demo, not much is happening, as there's no core-specific RAM, ROM, or devices, and the on-screen menu is also pretty basic. The Hello World example will go a bit deeper. Instantiated by the core is the clock_GAN component, in which you will put all the clocks you need for your core. We will also have to make sure to handle clock domain crossing for each clock, but we get to this later as the Democore only has one clock. The wrapper to the MiSTer core is called iMain and resides in main VHD. When you look at the output ports of main VHD, the power of the M2M framework becomes apparent. The core only needs to output some retro video signal and 16-bit PCM audio to the framework, and this will take care of HDMI and pulse density modulated 3.5mm audio output. You can also see that the MiSTer core can happily live in its own bubble without having to know what the framework does. iMain instantiates 2 components by default, the MiSTer core, which is the Democore in the example, as well as the keyboard. We will take a better look at the MiSTer2MEGA when we start with the real porting. The keyboard provides a simple interface to the MEGA65 keyboard, and in it you will be able to implement the mapping logic you need for your core. It runs in the same clock domain as the core, so it can be directly wired to it. For the Democore, the keyboard will simply send a signal that has 1 bit for each key, so essentially a 80-bit signal word. Config VHD controls all the things the user of the core can control and configure. It is synthesized into a ROM that is wired to QNice via the framework. For now, you need not to understand what everything does. There are lots of comments explaining the contents. Make sure to stay away from sections marked as do not touch. The Hello World example will explain this and show how you can define new menus. Globals is used by both core and framework and contains basic constants that you will need to change according to the setup of your core. This is the speed of the clock, the resolution of the screen, virtual drives and ROMs, and audio filters. How this is done will be topic of a later video. And this is the whole layout of the M2M framework, including the Democore. When you start porting a core, it is recommended that you take another look at the files on your own, to clear up questions and understand the connections better. In this episode we built an M2M Democore, tested it on the MEGA65 and took a quick look at the most important elements of the core and the M2M framework. Next episode we will do the Hello World tutorial, making some changes to the Democore to better understand how it works. You can find links to the framework and the demo repositories in the description of the video. If you have questions or corrections, please add them to the comments of the video, so I can answer them for everyone. For more complicated problem solving, you will find a bunch of people on the MEGA65 Discord, always willing to help. Thanks for watching. Bye!